In physics, it's Mr. Neff. Let's do the second video on projectile motion today. But before we do, what do you call a monkey who won't behave? I'll tell you about that at the end of the video. So here I have that same idea of that cannon being fired off of a cliff. Now, I'm showing the cannon, I'm showing a motion diagram for it that is in equal time intervals, maybe equal seconds, or probably for this, maybe just like fractions of a second, but equal times between the 2 points. Between the points, I am showing the cannonball at its different positions. And so we're going to say that the first cannonball is happening at time equals 0. So these reds are time equals, and then time equals 1, 2, 3, 4, 5, and finally 6 time intervals. Now I ask you to draw in the appropriate horizontal and vertical components of velocity. Now the very first one is only moving horizontally, and so I'm going to draw it that big. Now, I don't want you to think that I drew it over to the other cannonball. I just drew it arbitrarily far to the right side, and that's it. I did not draw a Y on it because it's fired completely straight out. If I drew it down like this, that would make me think that it was initially moving like that, but it wasn't, so I'm not going to draw that one. If I had a Y component like this, that would make me think that it was moving diagonally up, but again, it wasn't. So that's the complete picture for cannonball 0. Now, what I'd like you to do is stop the video, and I'd like you to try to draw velocity components X and Y, if appropriate, on cannonballs 1 through 6. Stop the video here. Okay, I really hope you stopped the video, and I hope that you drew the same velocity on each one of the X's. If you notice what I just did right there, I just traced my initial X a bunch of times so that then I can just put these vectors on each one of these. Why is that appropriate? Well, that is, one more. That is appropriate because in the X direction, there is no acceleration. That is just simply going to the right with constant speed because there's nothing to change it. There's no forces going forward. There's no forces going back. If this is a projectile, the only thing that's acting is gravity. Now, in the Y direction, though, you do have acceleration. And so by the time it gets out to 1 time interval in the air, it is moving down a little bit. And at 2 time intervals in the air, it's moving down a little farther. In fact, if it's really 2 time intervals, that should be twice as big as the first one, and 3 times as big, and 4 times as big. Now, I have a hard time with this blank background in the back, knowing if I'm really drawing it that many times. So that's why I'm just telling you. And then 6 times as big as what I did in the first place. And again, I don't know if that's quite right. So you can see in the X direction, we do not have acceleration. That's the question that I ask you up here. Is this cannonball accelerating in the X direction? Well, no, it's not. It's not because we have a constant size Vx. So I'm going to say all Vx's are the same size. What about in number 2? Is the cannonball accelerating in the Y direction? Well, you can see that there's nothing but change in the Y direction. At first, we didn't even have any Y velocity, and then we have more and more and more of it as we go. So, yes, the Vy's are getting bigger. Now, in question 3, is the cannonball accelerating? Question mark, without any qualifier, X direction, Y direction. Pause the video and try to answer that for it. Okay, I hope you paused the video there. And the answer is yes. The answer is yes because this, in fact, I like to say in class that the answer is yes, yes. Why would I say that? Well, see, the cannonball's velocity, the velocity, not the X component, not the Y component, well, it's the resultant of those two. At the beginning, it's just the same. The resultant is the X component because there is no Y component, but you can see that these velocities, the velocity at each spot is the resultant of the 2 components. You can see those yellow vectors that I just drew in there, they are getting longer. So I'll say the velocities are getting longer. That is, growing in magnitude, for sure. But they're also changing their direction. You can see at first the the velocity is perfectly to the side, perfectly in the x direction. And then it becomes more and more in the downward direction. It'll never get there because it's never going to get rid of its x component, but it is getting steeper and steeper down. So we can also say that the direction is always changing too. Either one of those on its own would answer that question yes, and so that's why I'm saying yes, yes. Here's a neat little example. Here we have a bank robber running across a rooftop, and he plans to jump, I should probably put quotes around the jump, to the next rooftop. He jumps straight out. So that is, he just kind of runs right off of the building, maybe even doesn't realize that there's no more building and just runs ahead. He jumps straight out from the building with a speed of 8 meters per second. Now it says, based on the numbers in the picture and your calculations, does he make it and why? Now before I turn you loose on this, I want to say that he's going to fall down to this height. Thing is, I don't know if his path looks more like this and he does make it, or his path looks more like this and he doesn't, or even if his path is just like this and he just makes it right onto that point, which I guess will count at he does make it onto the other building. It's still very, very far. It's 4 stories, and so this is not safe in either regard, whether he makes it or not. But it is, does he land on the other building or does he land between the buildings is really the question. Now, a good way to do this, I think, is to figure out how long it takes him to fall down to the height of the other building. And so when he gets down there, regardless of whether his path looks like this or his path looks like that, when he gets down there, it's going to take the same amount of time because gravity is going to pull him down regardless of how fast he's moving horizontally. So I think it's smart to come up with the time to get down there as a first step. And then the second step, I say, is to figure out how far forward or how much delta x he has. Why don't you pause the video now and use the numbers that are in the picture, see if you can get whether he makes it or not. Okay, so I hope you paused that video there. And so if I want to get that time, I know that delta y equals VOYT plus 1/2 AT squared. Now, I don't always put that y subscript on the VO like that, but I am this time just to emphasize that we are dealing only in the y direction and not in the x. So a common mistake is for somebody to put an 8 meters per second in for the VO. But as you can see, that's the horizontal. In fact, that 8 doesn't belong here. That belongs in the horizontal work, and those are independent from each other. We saw that in class. Turns out this VOY is 0 because he's going straight out. So if I had a vector like this, the VOY would be 0. Now, if I had a vector like that, the VOY would be something positive, right? Positive, blah, blah, blah. If I had a vector down like this, the VOY would be something negative. In this case, we don't have either of those. We're just going straight out. So a 0 in for that first term. So I can say that he's going 4 stories. Now, I converted that off camera, and I got a negative 12.192 meters. That's this 4 stories, 12.192 meters. And I made it negative because it's down. We'll say this is, and remember that is a 0 right there where that 8 was. That was a mistake. 1/2 times the negative 9.8 meters per second squared. And I hope you can still see that on top of that building, t squared. So you're going to multiply both sides by 2. You're going to divide both sides by 9.8. And then you're going to take a square root. And after you do those things, you're going to end up with 1.577 seconds. So that's the time it takes him to get down to that level. Now, most of the hard part's done. Now what I'll do is I'll say, all right, so then how far does he get? Delta x equals VXT, sure, plus 1/2 AT squared. But since in the x direction there's no force, no acceleration, that term becomes 0. Another common mistake is to try to put 9.8 in there for the acceleration, but you don't want to do that. You want to call that 0. So delta x equals Vx 8 meters per second times the time that I got from the other part, 1.577 seconds. And whenever you go ahead and into your calculator, you're going to get 12.6 meters. That's a bad thing for the bank robber. 48 feet turns out to be 14.63 meters, and 12 is not enough. And so unfortunately for him, the path looks more like the blue one and less like the yellow one or the red one. To make matters worse, when he gets down there, he still has his x velocity. So at all of those points, his velocity, well, it was that big, and it stays that big the whole time. And so he's got x velocity, x velocity, x velocity. And so that means, unfortunately, he's going to continue forward and end up smacking into the building down here somewhere. Bad day, bad idea to rob this bank. And our last thing for this video is the very famous monkey and hunter thought experiment. Now, the monkey and hunter is really famous, and there's a lot of different nuances to how the story is told. But in short, there's a monkey who is being aimed at, sometimes with a real rifle, sometimes with a launcher that shoots bananas or something like that. But regardless, there's a monkey that's being aimed at, straight line from something, source of a projectile. Now, the monkey, though, notices this and has a plan. The monkey says, as soon as the projectile comes out, I'm going to let go of the branch and I'm going to fall down. And the monkey thinks that this is going to be a safe plan, to let go of the branch as soon as the projectile comes out. What do you think about that? Stop the video for a second and get an opinion of the monkey's plan. Would the projectile hit the monkey, or would this plan work? I hope you're back, and you can see that our friends over at Physics Classroom have animated this exact thing. They have a simulator. It's a projectile launcher that shoots bananas at the monkey. And so they'll do a thing here where the monkey will be fired at in a gravity-free environment. So there, the monkey lets go, but since there's no gravity, he doesn't fall down, and neither does the projectile. And so the banana hits the monkey. Very good. Then, if you throw above the monkey with gravity on, as you can see, the monkey's going to let go, and the banana is going to hit above him. That wasn't the plan that I described before. This is the monkey being fired at, not at the monkey, but higher than. What I asked you to assess is to throw right at the monkey. And so if you throw right at the monkey, then what ends up happening is he gets hit by the banana. Why? Because the banana is going to fall off of its gravity-free path the same amount that the monkey falls from rest. See, with gravity on, that banana is going to follow this parabolic path. And since gravity affects everything the same, in the amount of time t that it takes for the banana to get over there, the banana is going to fall that far. Well, guess what? Gravity affects monkeys the same amount as it affects bananas, and so they're both going to have fallen the same distance. And so the monkey is going to get hit by the banana. Now, if the speed of the projectile is less, that actually doesn't matter. Because if you fire at the monkey with a slower speed, then that just means everything takes a lot longer, but it still gets hit by the projectile. All right, and so along those lines, what do you call a monkey who won't behave? Of course, you call it a bad boon. Bad boon, get it? See you next time.